Welcome, fellow chemists. Today's video is part 2 of writing binary ionic formulas, where we will meet the polyatomic ions. If you need a refresher on writing ionic formulas, click the link in the card or description. So what is a polyatomic ion? The prefix poly means many, so these ions, like nitrate, are composed of many atoms which have some overall charge. In the case of nitrate, the magnitude is 1, which is usually never shown. I prefer to write it as NO3-1 because we end up doing some math with that charge and it makes more sense to represent it as a number. A nitrate ion kind of looks like this, and the charge belongs to the entirety of the structure. Same would be true for other polyatomic ions like hydroxide, OH, and even the only common positive one, ammonium, NH4. As we make the formulas for compounds, keep in mind we cannot change the formula of these ions. Since we know the charge disappears, we can be more precise about what that means. As you know, binary ionic compounds are composed of cations and anions, and in this video, at least one is polyatomic. You also know formulas with ions of equal and opposite charges are the simplest to develop. The charges cancel, so we remove them, and then we move the ions together as they are. We do not alter the subscripts in any way. As the charges of the ions get progressively larger, they are still simply paired together as the charges cancel out. What we saw with monatomic ions does not change with the introduction of polyatomic ions. When the charges of the ions cancel out, we remove the charges and put the symbols together. But what about when the charges do not cancel out? Well, it depends. In the case of potassium and sulfate, the charge with one ion each is -1. Add another potassium, the charge becomes 0. This means the formula contains 2 potassium and 1 sulfate, which looks like this, and that's the easy case. With chromium and cyanide, we run into a not-so-obvious problem. With 1 ion each, the charge is +2, so we add more cyanide until we get to 0. The final formula now looks like CrCN3, except that doesn't work. It looks like we have 1 chromium, 1 carbon, and 3 nitrogens when we clearly use 3 cyanides. To fix this, we put the polyatomic ion in parentheses and the subscript on the outside bottom right. Anytime a polyatomic ion is needed more than once, you must do this. With calcium and borate, the charge starts out as -1. Add another calcium and it's +1. Another borate is needed, which means BO3 goes in parentheses. And finally, a third calcium brings the charge to 0, which gets us to the correct formula. If you saw part 1, you already know that the magnitudes of the ion charges become subscripts in the final formula. This means we can arrive at the correct formula by crisscrossing the charge values and turning them into subscripts. We do not put subscript 1s, and we do not include parentheses if a polyatomic ion is needed only once. So again, we do not need unnecessary fancy accounting to determine the formula, as a simple crisscross will do. This general form shows the parentheses around the anion, but it can also be around the cation. It's faster, yes, but beware cases like that of lead-4 and oxalate. When we get the formula, it looks good. However, the formula needs to have the simplest ratio possible. But with 2 2s and 2 4s, which ones simplify? Remember, we cannot change the formula of any ion, and oxalate is C2O4. If I change either of those subscripts, it is no longer oxalate. So that leaves us with simplifying only the numbers that were switched. And after doing so, this results in the proper formula. So let's wrap things up and attempt some practice. Remember that binary ionic compounds are composed of cations and anions with no overall charge. The formula of a polyatomic ion doesn't change when developing the formula, so it is placed in parentheses if needed more than once. The number of ions needed are written as subscripts except for 1, and when crisscrossing, remember to simplify subscripts in the final formula if they were not part of the original ions. There are 12 practice problems coming up, and refer to the ion list in the description if needed. If you have any questions, leave them in the comments. Best of luck, and as always, thank you very much for watching.